Okay, so as Kelly mentioned, what I'm going to talk to you today about is, I guess I'd call it the local gaseous universe in particular. What you're looking at here is kind of the extent in terms of the gas distribution that I'll be talking about. So within the local group volume, the galaxies, what they have in them for content, in particular the dwarf galaxies. I'll talk about that in the second half of my talk. And then the large spirals, the Milky Way and M31. I'll talk about those.
Earphones right there.
Oh, it's because I never put, oh shoot, that means I left my,
so in terms of,
I forgot to bring my.
So in terms of the Milky Way and M31, I'm largely going to be focusing on thinking about the halo gas, which is what I think a lot about. And so this is always something to keep in mind when you're thinking about the local gaseous universe. Most of the gas is actually thought to be not in the galaxies, but beyond it. You can do the same thing. I have some nice, young Zhang has done some really nice work starting to look at the dwarf galaxies in the local group. So in general, when I talk about the local gaseous universe for the larger galaxies, I'm going to be talking about the halo gas. And beyond that, what I'll bring in to consider is a local group medium. This is something that we haven't been able to do a lot of direct detection of that, in fact, none, but it is presumed to exist. This is the large dark matter halo that the Milky Way and M31 are embedded within. And I'll talk a little bit about the potential of having this extended medium that goes throughout the local group. Just in terms of some, I just thought, well, I need to give some brief intro. I know a lot of people here are direct galaxy people, but just in terms of why you should care in terms of gas content and galaxy evolution, I just pulled out a few reasons why you should care. One is when you're thinking about baryons in the universe, where they are, how the count works out in terms of within galaxies, that's definitely something that is relevant to what I'll be talking about in the first part of my talk today in particular and after. So this is a plot that shows the baryon fraction versus halo mass here. So we have halo mass on this axis, baryon fraction. And then in terms of the cosmic baryon fraction of about 16%, that would represent this dotted line. And so this is from the gray is when you have the stars and the gas for galaxies, just in the main bodies of the galaxies, and then this is just the stars. And so you can see, compared to what we would expect for the baryon fraction, there is a clear deficit within galaxies, and it gets even worse as you go to the lowest mass galaxies. There have been a couple of surveys that have basically started to find these baryons in the extended halos of galaxies. Cus halos, Cus dwarfs doesn't have enough lines to really do a baryon count, I would say, but they're starting to find that there are abundant detections of baryons in the halos. And then by coming soon, this is we have a couple galaxies in this mass range, and then we have a program that will expand this mass range even further in terms of at the lowest mass end, what we have in terms of how the halo gas or circumgalactic medium fills in the baryon content, and if we get up to closer to that 16% fraction. Another reason and relevant to what I'm talking about in terms of halo gas is that it traces both galactic feedback and accretion. This is something I did for a little review article thing I read, using the fun iPad apps. In the end, I was like, I can't believe I'm publishing this, but I actually like, when I look back at it, I actually like it, so I'm using it here. In terms of halo gas, if this is the disk, what you have within that halo gas, you're tracing the accretion of satellites. This is a satellite presumably coming in and being stripped of its gas, and the gas rains down and feeds the galaxy. You're tracing feedback from the disk, both any activity from the galactic center, either central star formation burst or AGN activity, and then this would be like galactic fountain material coming out. And then you're also tracing the accretion of gas coming in. And so in terms of gas and galaxy evolution, the halo gas or the CGM. And by the way, I'm pretty sure CGM, we're not sure exactly, I'm not sure exactly on this, but I think Greg Bryan may have coined that term. It's used generically instead of halo gas. It was not a term that was widely used when I did my PhD thesis, and I'm pretty sure Greg Bryan might have been the first one. So you can thank him for that acronym, circumgalactic medium, CGM. And so here you can see it's also tracing the inflow of gas from the surrounding intergalactic medium as well. So it's really the base where you can kind of track everything that's going on within a galaxy for the feedback and what its future is. And related to future, the gas in galaxies is dictating the future star formation potential. Of course, we would not exist unless there was ongoing gas accretion. The the sun is a second generation star. The star, when you look in the past at Milky Way-like galaxies, they're going through fuel so quickly that they basically would be by far red and dead today if they did not have that ongoing accretion. So in the fact that we have our sun is thanks to the fact that we do have ongoing gas accretion in process. And this is an issue throughout time that is interesting in terms of how this gas accretion is happening to continually fuel the future of star formation. What this plot is showing, and I'm sorry if some of these axes are too small for the Zoom screen. This is showing you redshift versus the mass density of the stars. The purple is the stars, and the green is the gas as traced by neutral hydrogen. And the point here is that as you go through time, there's an increase in stars, but the amount of gas, coal gas, stays relatively flat. So this is an interesting question. I think Alberto could say more about this in terms of the link to the molecular fraction as well. But this is just a very interesting point in terms of thinking about gas and the future of galaxy evolution and how that all plays out. Presumably what must be going on here is that some of the extended gas that's warmer in nature is continually cooling to have this continual increase in stars while the overall gas density stays relatively flat. And obviously you can see the points in terms of the gas are a little bit underpopulated in this area. Oh, and sorry, this is with look back time versus redshift for those of you that prefer to think about look back time in the universe. And what'll help here, the Chile survey should add a nice point right around here. So that'll be nice because that'll be a data set that's detecting the gas in emission and can say, and where most of these are just damp Lyman alpha absorbers stats for that. So this will be a nice additional point. And the Chile survey is led largely by Jacqueline Van Gorkum at Columbia. Okay, so in terms of the questions I'm going to talk about here that are somewhat related to some of the intro material I showed you. First, I'll start out just saying something about what we have for a baryon count, including the halo gas in particular of L-star galaxies, but really where my focus is going to be is the Milky Way, but I'll do a contrast to what has been found by surveys like the CosHalo surveys. And then the second part of the talk will be on how the different gaseous baryons of different mass halos interact, and in particular, looking at the dwarf galaxy, what leads to the quenching of dwarf galaxies, and what is the role of a group medium in that quenching. Are there any quick things people want to bring up at this stage in terms of intro material? I almost, I thought about integrating Zoom polls. They worked really well for class. It just didn't seem like it naturally fit here. So I do not have Zoom polls, although I do like the idea of making these more interactive. So have you guys had people give talks where they've made you do Zoom polls remote? No one I can see is nodding. Okay.
I don't think so.
Yeah, I should have done it then. Uh, okay, so let's look a little bit at an L-star galaxy and what the baryon budget is looking like right now, which in terms of the this particular pie chart, this was created by Jessica Work, and it's related to her result as well as the Cos Halos group in general. And what they find basically is that, you know, we have the stars, the interstellar medium, hot corona. This value I would say is quite uncertain, but they have the hot corona here at 10%. And then here is the big surprise that this survey has found, and others have found significant amounts as well, that the circumgalactic medium, or the halo gas of a galaxy, is harboring basically 50% of the baryons here. And it comes in both a cool form and a warm form, where the cool is gas at about 10 to the 4 to 10 to the 5 Kelvin, and the warm is gas about 10 to the 5 to 10 to the 6 Kelvin in terms of how they're accounting for it here. So this is immediately like, oh, we found the missing baryons, or at least most of them. There are definite uncertainties in getting these mass results. But the other thing is just, what do we have locally in terms of that baryon content? Can we confirm the Cos Halos results? And so one place you can look is our own Milky Way. And so I've been involved in several papers that have been thinking about what we have for halo gas around our own Milky Way. Just quick background on the Milky Way, just this is our spiral Milky Way. It's part of this local group of galaxies, a very loose group still coming together, with only one other large spiral. And this is a plot from Bland, Hawthorne, and Gerhard, which shows you the relation compared to other galaxies. And here, what they have, the cross is the Milky Way. And then all the points are, the red dots are Milky Way analogs with the same rough stellar mass and star formation, right? And one interesting point they make is that, so you have this cluster. It also shows you what relative to the red and the blue galaxies overall, where the Milky Way roughly lies. It's been known as being close to a Green Valley galaxy when you put it on this type of plot. But the other interesting thing in their review here is how much things spread out once you go into color space as well. So in terms of, there was a question at the KITP CGM meeting about whether the Milky Way is typical of L-star galaxies. And I would say overall it is, but it really depends on how you actually define a Milky Way galaxy, etc.
Sorry, Mary, can I ask a quick question?
Please.
Yeah, what were the contours here and in the previous plot?
In this one, I actually don't know. I don't remember. I grabbed this a while ago, so I don't remember exactly what the contours might.
I think it's a density of points typically.
Well, it just doesn't look like it's the Milky Way type point, so I was just wondering.
The red dots are the Milky Way type points. Sorry, but the contours are related to what Alberto mentioned, I would guess, in terms of how many galaxies are in the survey in all those different areas. So most galaxies in SDSS are either in this clump or this clump, and then there's less, you know, between the ranges overall. So there's less overall than Milky Way property galaxies than in these clumps specifically.
Okay, thank you.
So in terms of thinking about studying the Milky Way halo and assessing what it has for its CGM or circumgalactic medium, you can immediately look at a plot like this. This plots all the background quasars that were available from COS. This is 2019, so this would have improved even more. And every one of these sight lines that's been observed with the cosmic origin spectrograph on the Hubble Space Telescope that detects this circumgalactic medium gas passes through the Milky Way halo. So you can imagine right away, we have a wealth of data available to us here. In this particular study, she adopted only those that had a signal to noise greater than 10, where you have better signal. The other thing that's interesting, and this is related to a proposal I'm on this round, is the clear deficit in the plane. And so this is definitely limiting our ability to assess the full distribution of the gas and how it's distributed around our Milky Way. In terms of thinking about how this might differ from an extragalactic sightline, so when you have the background light source to the observer for an extragalactic sightline, you're going to pass through it like this. So for the Milky Way, we're within the disk, right? And we're looking out at this source. So that leads to a somewhat different path length. Path length is not exactly a factor of 2, but there is a somewhat different path length that needs to be taken into account. But the other factor that needs to be considered is we have the obscuration effect of the gas in the disk always that we need to think about. In particular, we can look at what has been observed for both our Milky Way and other galaxies. So just to explain this plot, this is showing you our Milky Way, all of the, this is the galactic longitude versus velocity, and the gray is a simulation showing where the circumgalactic gas is. And then the points here represent the observations. So in this plot, then just focusing on this side, you can see that much of the circumgalactic gas in this simulation is in this range where it's around 0 relative to us, and that is a difficult range for us to assess because we're within the disk and the gas right around us is at 0 kilometers per second relative to us. So that's where we're potentially missing a lot of gas when we observe the Milky Way halo. And then this is the plot for the extragalactic sightlines, the gray being the simulation and the points being all the observations. And this is making the point that around 0 relative to the galaxy is where a lot of the circumgalactic gas is being detected, right? So it does indicate that there's a lot of circumgalactic gas that's going to be close to 0 kilometers per second relative to the galaxy that we would be missing in terms of when we're observing from within the Milky Way. So related to addressing this, both assessing the structure of the Milky Way halo gas and addressing this issue of, what are we missing in this velocity range, we have a survey called Quastar. This was a proposal initially PI'd by Josh Peak, but Hannah Bish is the graduate student who's the clear lead on the paper that's just been published on this. It's a 2021. It is now officially published. And the goal of Quastar is comparing the absorption detected for matched quasar and stellar sightlines. And I'll just show you a plot that shows this a little bit better. So the idea here is that we have a star that's within 10 kiloparsecs of the disk, and then we have a quasar that's very close to the star on the sky, which is at a much larger distance. And so then you see what you detect along the stellar sightline, you see what you detect along the quasar sightline, and you subtract the two. So this would be a possible example where the red is representing what you got along the stellar sightline, where you're getting just the disk, and I'm just making sure I'm addressing this. Yeah, right. Where you have just the disk halo interface region, and then for the blue, you're getting the quasar sightline, which is that disk halo interface region, as well as all of this circumgalactic gas as well. So you can do a differencing experiment and then extract what is where the gas is in the Milky Way halo, where is it in this extended region, and also recover getting that 0 kilometer per second halo gas out as well. The design of the experiment, then, it was 30 halo stars that were matched with the quasar sightlines. And we were looking at carbon-4 in particular. The doublet factor is useful for confirming the lines. And this has been detected in the halo of other nearby galaxies. But also the reason we went with this is there's some really useful work by Richter et al. I think he's the main one who showed this, that the variation of the carbon-4 on these types of scales was basically negligible in terms of if you're just thinking about two quasar sightlines and you're looking at high velocity absorbers, there was very little variation overall. So in terms of worrying about the clumpiness factor and how that could play in to this experiment, that was evidence that if we had them within 2 degrees of each other, that they should be larger than any type of clump scale typically. And then, as I mentioned, what we did then is what Hannah did this largely in terms of having the two, the halo site, the quasar sightline and the halo star sightline, quasar minus star. This would be an example where you detect the CGM gas, and this would be an example where you do not detect the CGM gas in that. So it was a pretty straightforward experiment in terms of trying to detect exactly where the gas in the Milky Way halo is. And it was somewhat surprising that what we found is that when you looked across the sky, so this is showing you, I know you can't read this, I apologize. So this is showing you the difference in the quasar and stellar sightline basically, but darker colors represent there was a significant difference, where the lighter colors, there was not a significant difference between the quasar and stellar sightline. And overall, and on the bottom, we have this difference versus galactic longitude and galactic latitude, where the gray represents where we think we can detect the difference is significant. And so overall, there's very few sightlines that showed a significant detection in the halo beyond 10 kiloparsecs. Or 8 kiloparsecs is where most of the stars were. So 8 is what we have here. So that indicated that there was something strange about the Milky Way, that the covering fraction of this carbon-4 gas beyond the 8 kiloparsecs is very, very low compared to what we find in other galaxies. And this is showing you a plot that has covering fraction from a whole combination of work for other galaxies. So this is R over R Vir showing you covering fraction, which gets to be quite high. And these are the points from the Milky Way. This is when you just use low velocity Milky Way. And this is when you also include some of the higher velocity line observers. And the point is here because of the 8 kiloparsecs, but in terms of the covering fraction, it's going from 8 kiloparsecs all the way out in terms of where that gas is. So overall, we have a low covering fraction for the Milky Way compared to other galaxies. And you can go on to think about this in terms of a mass, not necessarily just with the carbon-4, but this is work, again, Yongzheng has thought about in terms of extrapolating this to a mass. And what she does in terms of that census is consistent with what Hannah Bish found, that there isn't much there. And that was using all those quasar sightlines and using the standard types of models that are used for COS halos, et cetera. And what we find is you always have this greater because of the uncertainties in the mass, but it was more like greater than 10 to the 9 solar masses within 75 kiloparsecs. And for COS halos, this value is huge, right? It's greater than 2 by 10 to the 10. So it definitely, the Milky Way results overall, combining the work, looking at all the sight lines and assessing how much absorption you see, which I haven't talked about. That paper was a few years ago now. And then this new result from Hannah Bish, where she uses those matched stars and quasars, is all pointing that there's something either odd about the Milky Way or something odd about COS halos results in terms of there being a lot of this warm CGM gas present. So what are the reasons for that? It could be many things. It could be the Milky Way is in the process of quenching. It is kind of going down into that Green Valley type region. It could be that the carbon-4 doesn't trace a CGM in our case because the baryons are in a hotter phase. This is related to what I'll talk about later. We do live in a local group. The environment of the Cos-Halos galaxies, don't think the paper has been, I know they're assessing that, but I don't think there's been a paper out on the environment yet. So this could be related to the fact that we live in a local group. And the other thing that's interesting to consider is that the warm CGM could actually be in a giant flared disk. And this is, I don't have the proper reference there, but I think this was originally really pushed forward by Joel Bregman. And I think initially people were like, you know, but the more we look at it, because it's the same situation for extragalactic sightlines. If you have a huge flared disk of ionized gas, all these sightlines going through it are going to detect it in the same way, basically. So this is a possibility, and we don't have the low latitude sightlines yet to fully assess if we are in a situation where the ionized gas is in this extended warm flared disk there. Alberto, go ahead.
I had a couple of questions. One was, what is the interpretation of the sightlines where you see more gas toward the star than toward the background quasar? Because you got a few of those, no? So negative.
Yeah, so the ones that have more, one of them, I know for this one, this is a known low velocity halo cloud. This was found in an old paper by Josh Peak looking at dust content of clouds and such. So one of them is that, right? Because we actually know that we're also missing that low velocity gas when we look at like the high velocity clouds and stuff. So one of them is indeed associated with this kind of cloud that, even though it has a low velocity, is thought to be in the halo at some level. Once you go on this particular plot, I can't remember if she includes the high velocity gas, because you want to take a census of, you're looking for that missing low velocity gas, but you also want to take into a census this other high velocity gas that counts as being within the extended halo. But of course, some of the sightlines have material from the Magellanic system in them, so then you do get a detection of the higher velocity halo gas in there as well. And that's related to the 2 points here. So this higher point is if you include the higher velocity halo gas as well. And this is just for that gas that's close to 0 kilometers per second with that differencing. But in terms of where that excess gas is exactly, I wouldn't say, for this, we know some of it's associated with the Magellanic system. The stuff that's detected at low velocity, as I mentioned, there's that one low velocity cloud. And then I know there's at least one other that has low velocity. I don't know that we know where that gas is.
My other question is, do you get interesting kinematic information about, like, you know, rotation of the halo or something like that from these?
Yeah, we haven't used it to think about rotation, but that's actually something now. Enrico Ramirez, I think his name is a postdoc with Josh Peak that is exactly going to be using some of these data to think about the kinematics and whether you can think about that extended ionized gas layer and the kinematic signatures it would produce with these data. This has been looked at, of course, the Frantinelli group, I think it's a Marasco et al. Might be the first author in terms of they've thought about the sightlines and thought about seeing a lagging halo for the Milky Way using old data. This is a maybe 6 years ago paper, but yeah, we are going to think about that more going forward as well.
Yeah, I think there are also papers by Hodges Clark.
Oh, so that is very interesting. That's the hot gas. That's the X-ray gas that he looked at in particular, where he sees that signature of halo rotation using the X-ray data. Yeah, otherwise, no one's really tried that so much beyond, because we don't know exactly where it is and such. I mean, we do think the stuff that's relatively close by does have that co-rotation and has some lag. No one's really tried to take that much further out into the Milky Way halo just because the exact location of the gas is pretty uncertain. But I think more can definitely be done on that though at the same time. So.
Thank you.
Okay, just to tie it back in terms of the baryon census then, in terms of where I started. So what we're seeing here, the evidence is pointing that the Milky Way does not have a huge fraction of baryons. For the hot gas, I'll just mention this work. Hot gas is difficult to pinpoint, in particular for the Milky Way living inside of it, but this is some work by Lee and Bregman and Miller and Bregman, where they did some fits to the X-ray lines. This is showing, and created some models where they also include a rotating halo and think about what the enclosed mass would be. And in general, they're finding that this hot gas has a mass less than 5 by 10 to the 10 within 250 kiloparsecs. And this is using a metallicity of 0.3. So go to a higher metallicity actually means less mass. So depending on what you think the metallicity of the gas would actually be. But this is at least an estimate. And so then if you go to that pie diagram, just to make the point, we can think about the stars in the Milky Way, about 5 to 7 times 10 to the 10, the ISM. I didn't adjust percentages here, I just have the mass numbers. But ISM 4 to 8 times 10 to the 9, hot corona, less than that. And then if you're going out within the extended halo, that number I showed you before was within 75 kiloparsecs. So if you go out to 250 kiloparsecs, you maybe get up to a few by 10 to the 10, but you're not at the 50% level by any means, right? You're more maybe similar to the stars here in terms of how much we're finding in the halo of the Milky Way. So it definitely harbors a decent amount of baryons, but so far we're just not finding them for the Milky Way like they're being found for other surveys. Another example, you say, well, that's the Milky Way, so let's have a quick look at M31. This is not my work, but it is consistent with what we get for the Milky Way. So M31, slightly larger in mass in terms of the stars and gas. What do we have for the CGM? So this is the work of Lehner et al. I guess it's called the Amiga survey. So what they do is here's M31, and then they have a whole bunch of quasar sightlines around M31. I do want to make the point here that they do have to deal with a lot of contamination doing this work, and I am definitely looking forward to when they get more sightlines in this direction, because as you see here, this is where the Magellanic Stream passes through, and the Magellanic Stream lies at in this region. Unfortunately, Magellanic Stream has very similar velocities to the M31 system. So you have a lot to deal with contamination here. But overall, what they're finding is that they're do find about the same as what we're finding for the Milky Way. If you're interested in the contamination issues, I'm seeing I have a couple of slides here, which I'm going to skip related to that because I don't think most of you are interested in that. But overall, in terms of linking in M31 and what you have in terms of the stars, gas, bit more hot gas, who knows for M31. I'm not gonna, I don't know if anyone knows someone who's tried to assess that. I'd like to hear, but I don't know that we have an assessment. And then for the halo gas, again, they're actually finding something quite similar. They find about a few by 10 to the 10 out to the virial radius for M31. So again, both M31 and the Milky Way appear to possibly be CGM outliers from what is found more generally in surveys like COS halos. So a few things you can ask. COS halos is not exactly at a redshift of 0, so maybe this is a generic z equals 0 problem. When we look at other nearby galaxies, we do see we've done very deep surveys, for example, in neutral hydrogen, and we aren't typically seeing the kind of gas we would expect based on things like what COS halos found. So maybe this is a problem beyond the Milky Way and M31, and it's a z equals 0 problem. Maybe there's an environment link. I already mentioned this in terms of the local group. And the other thing is the distribution of the CGM halo gas too complex to actually do this type of comparison? That's related to the very simple way we're currently getting masses, right? And maybe, you know, if we have some type of, for instance, that flared disk structure overall or something, maybe it's just not appropriate to kind of try to do that type of comparison. So there's a few options here. If other people have other suggestions, feel free to jump in. Otherwise, I'm going to jump into the next section of the talk. So if there's more questions at this stage, I'm happy to take them. Or if you want me just to go back to a slide quick.
I have a quick question, Mary.
Okay.
Do you know, is there an estimate of the variance of the CGM from cost halos?
Not that I know of, Ari, just because, you know, because they only have one sightline per galaxy, right? They kind of, they're collating all their results together.
Yeah, but that's really the comparison you need, right? Because you have one object to compare, not to the mean, but to the variance of the population.
Yeah, I do think there's something that could be done more with taking z=0 galaxies in general, and doing a larger comparison. Okay, I'm gonna shift gears a little bit here and just say something about dwarf galaxies now. In particular, I'm talking about the dwarf galaxies you saw in this picture, but also I'll have a slide that summarizes that a bit more, and how they can be used in terms of understanding that diffuse medium, but also the evolution of dwarf galaxies overall. One thing that I find quite interesting is to look at the dwarf galaxy count throughout time, and I expect this will keep going up in terms of if you take the count that are galaxies that are definitely defined to be local group, right? Well, almost certainly based on the distance determinations. You know, back in 1971, there were 14. The Mateo review in 1998 had 40. And then now McConaughey and Simon reviews in particular, we're up to 95. I expect this will continue to go up as we have new surveys, or maybe not. Maybe within the local group volume, we've kind of gotten to the faint end. I don't think that is true, though. We have clear limitations once you go beyond the virial radius of the Milky Way. So beyond about 300 kiloparsecs, most of the optical surveys have severe limitations in terms of detecting the optical components, at least. So I think it will keep going up. This is a paper that is currently in press. It is on AstroPH. It should be in press, but they are having some troubles with the tables. The tables have a lot in them. There are 119 galaxies in there, and we've assessed the gas content in all of them. When I say gas content, I am talking about the atomic gas, or the H1, forgive me, Alberto. But in terms of these dwarf galaxies, molecular gas is, and ionized gas in terms of, at least in the disk, is not a large fraction. The atomic gas is by far the largest fraction for these local dwarf galaxies. And just to give you some ideas of the mass range, we're all the way down from 10 to the 3, so 1,000 solar masses, to 10 to the 9.3, and this is a range of gas masses for those that have it. So these are very clearly the smallest known galaxies in the universe. And basically what we went to do with this paper is basically to redo a paper that was done back in 2009 with the discovery of all these new dwarf galaxies, and also assess what the local group environment could potentially do to the gas content. So this is the old plot. This is from Gaseous and Putman 2009. And what we found back then is that within the virial radius of the Milky Way and M31, all of the galaxies tended to be quenched. So the quenched or not have gas. So these are the little arrows down. Those are indicating they don't have gas. Where beyond the virial radius of the Milky Way or M31, they had gas. And this had been pointed out by a few other people as well, that this was starting to show up as interesting, that there was this clear distance relationship. So we can redo this now, and it looks quite different. So this is also, this is on a linear scale, and I'll zoom in here. So now what we have is, this is the Milky Way is the blue, and Andromeda M31 is the red. The line represents an approximate virial radius, and then the shades represent a range of possible virial radii. The modeling work was done by Adrian Price Whalen, who you all know very well. And all of these open symbols represent that they do not have gas, and all of the solid symbols represent galaxies that have gas. So overall, what we find again is that 85 of the galaxies within the virial radii of the Milky Way and M31 do not have gas to quite deep levels, generally deeper than any of the detections of gas. And then beyond, they largely have gas. So there's a very clear distant dependent quenching mechanism going on here, even as we now include many, many more galaxies in the sample. And this is just zooming in to see the Andromeda and the Milky Way dwarf galaxies and all the limits there. So in terms of what that distant dependent quenching mechanism is, there's many different ways people have thought about how dwarf galaxies are potentially quenched. Tidal forces are generally not thought to be strong enough because of the dependency going out to large radii. Also, the stellar distribution is not typically disturbed in these dwarf galaxies. It is for a few, but not that many. Star formation, stellar feedback, that's also been considered as a potential important way to blast the gas out of galaxies. Generally, the work of people like, I know Andrew Emmerich did a recent paper with Mordecai McLough, that it's not enough on its own, and also it just would not reproduce this distance dependent. At the same time, I'm going to skip the last point of how it could be related, actually. Reionization, so this is a big one for the small ones. So then the question is, but would this be distant dependent? And generally, you would not expect to get this kind of distance dependency with reionization. And then, so the thing that we look more into, and this is the same thing we did previously, is the Ram pressure stripping, and assess, is that circumgalactic medium around the Milky Way and M31 dense enough to strip the gas from the dwarf galaxies. And a way you can look at this is just initially just using a simple Gunn and Gott criteria. So here's just the halo density required at paragalacticon for instantaneous stripping can be written as this. And the reason we can do this for so many right now in a nice way is because we now have proper motions or orbits for many of them. So what we can look at is the minimum gas density that is required to completely strip a dwarf of its gas. And with that, then we have a measure of the dispersion, velocity dispersion within the satellites, and we have a clear measure of the motion of the satellites now with the Gaia results. And this is what the plot looks like. It's coded by velocity dispersion to give you an idea of the mass of the galaxy. So the red points are the least massive, and so they take the lowest halo densities to actually strip them. And then up here, you can see a galaxy like Fornax is one of the most massive, and so it takes a higher halo density to strip them. So then the next thing you can think about, okay, that's nice, but these densities mean nothing to me. So let's have a comparison. I'm not going to bring in the observational limitations on the halo density right now, but they are consistent with what I show you for the simulations. So we did comparative simulations in terms of what they find for the halo density of a galaxy. So this is, the blue is from Foggy, and it's a lower mass galaxy at a slightly higher redshift. So we did not focus on this as the main comparison point because the galaxy total mass was only 4.9 times 10 to the 11. The red, it is higher resolution though, and it's interesting to be a comparison to see the range of possible densities they get in that higher resolution data. And then the red here shows you the galaxy that is the mass of the Milky Way at z equals 0. This is the work of Zhang et al. And this is a picture representing that simulation, although not at z equals 0. So what you can see here is that many of the galaxies are consistent with being stripped, given at Paragalacticon by a halo density. So 80% of the galaxies with proper motions are consistent with being stripped by a Milky Way halo medium. So this is, and this is even just thinking about what would be for instantaneous stripping. So in terms of what else could play a role in terms of stripping some of these that slightly lie beyond. Compressed gas is so what happens is you have the galaxy come in and the foreground, and Stephanie, I'm sure, has told you a lot about this, so I don't think I should say too much, but you compress the gas here, and then when you have that compressed denser gas, you can trigger star formation. Then you're going to have more stellar feedback and you'll loosen the gas. That's going to aid in the stripping as it comes in. You can also have the CGM is a clumpy place, so you can have the galaxy pass through an overdense region, or the fact that there was denser halo gas at early times when many of these were presumably stripped given their star formation histories, and that can also help with the stripping. A rotating halo, this could help or hurt, right? Depending on the angle that it comes in relative to the rotation, this could either help or hurt that. I think there's a nice paper, I think it's Smith et al. From the Foggy group on this. And then finally, the continuous stripping throughout its orbit is also going to play a role. What I was showing you there was that even just that instantaneous stripping at Paragalacticon was enough to strip 80%. And then if you add in these other factors, the other 20% should be stripped relatively easily as well. So related to the last point, continuous stripping throughout its orbit, I want to go with the remaining time to talk about the local group medium. So what about that local group medium? Because when you think about the dwarf galaxies on their orbit, you know, they're passing through the Milky Way halo, but many of them are going to also go beyond the virial radius during their orbit, or they'll come when they first come into the local group, etc. So what about the potential stripping role of a local group medium? And just a little bit of background, there isn't a lot in terms of simulations of a local group mass scale. There is a group now, it's Philip Richter's group. Martin Spar is one of the leaders of this, doing these local group simulations. This is an older one that I like a lot. This is of Nusa et al., where here would be the Milky Way and Andromeda, and this is gas, the hottest gas, temperature greater than 10 to the 5 Kelvin, and then going to cooler gas, and then this is the neutral hydrogen gas. So it's showing you that indeed, as you would expect, the local group itself is filled with this extended diffuse gas. And so you can think about what potential role that extended diffuse gas could play in helping this overall stripping process. And in particular, what's of quite a bit of interest is if the dwarf is passing through the region between the two galaxies, because that's going to be some of the densest area. And that's shown here. This is showing you the NUSA simulation. Just focus on, this is going in every direction, going out from the Milky Way, this dashed line. And then the solid line is if you go in the M31 direction. And in particular, you can see that it stays not too much below 10 to the -4. And so many of the dwarfs could be easily stripped passing just through the local group medium if they pass through that central region. And Adrian tried to look at this. The data isn't good enough to say, you know, how many actually pass through that region between the two galaxies. And this plot doesn't look like it showed up, but this is at apocenter, the kind of densities that would be needed for stripping. You can see many of them still need quite high densities, but there is also a population that could be more easily stripped or at least benefit from the continuous stripping as it passes through a local group medium. So what we did is we assessed the sample in terms of a local group surface. So this is showing you the Milky Way in M31, and this ellipse around it shows you the local group surface. This is a model Adrian put together, and then the red is the non-detection, the blue are the H1 detections of the dwarf galaxies. This is two different projections, XY and then XZ here. And so when we look at this, we get something like this. So this is distance from that local group surface. So here's the 0 line here. And then these are all the non-detections, and these are the detections. And indeed, things get even. So there were 80 within the virial radius of the Milky Way and M31 that did not have gas. When you use that local group surface, with the same relative masses. This model uses exactly the same masses that were used to get those virial radii for the other. Indeed, you get better, right? But not by a whole lot. It's like by 5 galaxies more. 85 galaxies are without gas within the local group with that. So that is interesting in terms of the relationship gets a little bit better, that more of the galaxies without gas are then within that local group surface. And again, by the local group surface, so it's either, kind of between the two or maybe slightly on the edges here is what we're looking at. This is somewhat limited in terms of projection. The other thing that's interesting is when you look at these particular galaxies that have gas, so either generally lower mass or further in to the local group, they all have somewhat disturbed gas. And I'm not saying this is definitely due to ram pressure stripping, but this has been claimed by several authors that it is due to that. Some examples are even a recent paper on Leo T, where we notice this from other data as well. It actually does have this kind of elongated structure. And this is a galaxy that is very low mass and at about 420 kiloparsecs, so beyond the virial radius. LGS3, which is right at the edge of the virial radius, also has very irregular structure. I'm not sure I'd say it was head tail. I'd have to look at the data more clearly. But again, so it could be something going on here in terms of these are also in the process of losing their gas at some level. There's also a paper claiming Pegasus shows that structure from being ram pressure stripped. Phoenix is in galactic emission. It's kind of a mess, but it also shows some nice structure there. So it could be something there in terms of these galaxies towards that edge of towards the local group surface there, which have gas showing some active signs of stripping. The Magellanic system, it's much easier to explain its long extended ionized tail if it also, you need the interaction of the dwarfs themselves, and Sarah can tell you a lot more about that. But once it's loosened up and you have the system coming in, if it's coming in for the first time, having some extended local group medium would also help drag that gas out behind it. More evidence for a local group medium. I'll just mention there are absorption line sightlines that are local group curious, I use the word for. This was found by Sembeck et al. And people keep coming back to this because even with all the incoming data, there's certain absorbers that do not make as much sense in terms of their position velocity and the pressures derived in terms of where they belong. So a local group environment may be significant. The other evidence that was one of the motivations for me to push forward on this is the SAGA survey results. So what this is a deep optical survey around Milky Way analogs. And what they're finding is that 108 of 127 of the satellites they detect are star forming, right? So this is 86% of their sample is star forming. So that means that they should have gas, right? Like they're not quenched. So in terms of what the local group has, it only has 29% star forming in that. And so this continues. They just have another paper too that was fully consistent with those results. So this remains an issue in terms of whether there's something special about the Milky Way and M31 in particular. Maybe it's the fact that they're within a local group and the local group is playing an additional role in that stripping. But I do want to point out other local deep optical studies are finding similarity to the Milky Way. This is in particular nice work where Carlston et al., also with Jenny Green, are getting distances to satellites and finding consistency with what we have for the Milky Way and M31. And there's a student, Jingyao Zhu, looking at what we find for the gas content of cytolites for local spirals. So we'll look forward to what she finds in terms of going into using the gas instead of the stars to find what we see, if we get a parallel with what we find for the Milky Way and Andromeda. Okay, I'm gonna, one more thing I'll mention, because I think it's interesting in terms of wrapping up the mechanisms. So in terms of the mechanisms and going back to our plots, and I can show you the plots scaled by luminosity and total mass if you want, but otherwise I think it's about time to wrap up. But I do want to say one thing that's been brought up here is whether we will detect more galaxies out here that do not have gas. And I do think that is somewhat of an open question. We are not, there's been numerous surveys, we are not definitely finding galaxies with gas within this radius. So I think that's pretty solid, that it's very limited within this radius, but it is possible that we will find galaxies without gas further out yet. So that's to be determined, I would say. There are predictions from simulations that there'll be missing dwarf galaxies in the field. This is within 10 megaparsecs. This is what's observed in terms of the mass density. I guess they do it by with circular velocity, mass density, in terms of what's been observed, and then what they're predicting, right? And so here you can see they're predicting that there'll be a lot more low mass satellites not satellites, field dwarf galaxies that will be detected with time. And if they're found, this is a lot of words, so I'll say this out loud, but if they are found, this is supportive of reionization playing an important additional role. Although one thing that's also should be known is that simulations find that 40% of the galaxies between the virial radius of the galaxies out to a megaparsec are expected to be these backsplash galaxies, which have already come in and are shot back out. So it's not, we can find a few without gas out there, and it's not immediately saying, oh yeah, we see it, we definitely need the reionization, et cetera. We also have to consider that we'd have a large fraction of backsplash galaxies there. Okay, and so just to summarize that particular work, we're finding new gas limits for the local group dwarf galaxies, and this is available if you're interested in these numbers. This is double the dwarf galaxies since 2009, but one interesting point, as I mentioned, we are not finding galaxies with gas closer in generally. And there is this clear relationship with the Milky Way and M31 yet, but there's also even a somewhat stronger relationship with a local group surface. And the Gaia proper motions are particularly useful now that we can actually look at the actual motion and assess the role of ramp pressure stripping. And just to have something on the future, of course, for the deep optical, we're all looking forward to LSST. I also want to point out in terms of the gas distribution, there are future ASCAP surveys going on now, which is an Australian precursor to the Square Kilometre Array that are now producing data that are going to do a great job in looking at the gas and finding new galaxies with gas. So I'll go ahead and end there and take any questions. Thanks.
Great, awesome. Thanks so much, Mary. I suspect we're going to have multiple questions and folks that want to have discussions. So why don't we try the raise hand feature, especially if there's someone that hasn't asked a question yet.
I'll just stop share for now. And then if someone wants to look at a slide or something, I can do that.
All right, Rachel.
I was holding off to give more junior people a chance, but I'll ask my question since there were no other hands. So I just wanted to push on this puzzle, Mary, of you telling us that, if I understood right, so the Milky Way has a lower mass CGM than other galaxies of its mass, and yet we have so many more quenched satellites, at least according to the Saga survey. So that, that's the opposite Way, like the Milky Way is weird, but it's sort of weird in the wrong way. It has less CGM to quench all those satellites. So were you telling us that there's a different study that disagrees with Saga in terms of the number of quenched satellites, or how do you wrap your head around this? What do you think the resolution to this puzzle is?
That's a great point. I part of it is going back to whether the local group hotter medium is playing a role that we're not directly detecting with the Milky Way work. But yeah, the Saga results are curious that it doesn't fully follow with what else has been found, like by Carlston et al. And also with even, one of the co-authors of Saga's work herself, Marla's work in terms of finding, more galaxies closer, satellites closer to galaxies tend to have less gas, et cetera. So it's a little anti in many ways. So there's a lot to look into more with that. But I find the results fascinating at the same time. But yeah, Carlson in particular, he has a series of papers. He probably has come to CCA, would be my guess. But where he's looked at about 8 local galaxies and really done a good job of looking at the satellite census and their colors, et cetera, and is finding overall total consistency with the Milky Way and M31.
Okay, great, thanks.
John?
I wanted to ask, so the Magellanic Stream came up a couple of times, and the Magellanic System is obviously another way in which like the Milky Way is weird. And I just wanted to double check that in sort of the accounting of the CGM budget, if you include all of the Magellanic Stream, do you get up into something that sort of agrees with COS halos in terms of just the cool mass? Because there's just, my understanding is that there's just a huge amount of mass in the stream.
Yeah. Now I'm trying to remember those numbers offhand. So we do not include that in that particular. Let's see if I have the number here. Stop sharing screen. No, I don't have the number. Sorry, I don't have the number here, but I don't think we get anywhere near up to those numbers though, because if we go, I think it's something, it's 10 to the 8, and then I think it goes up to a few by 10 to the 9, if I'm thinking right, in terms of adding in the Magellanic System. So it's still not getting anywhere near like the few by 10 to the 10 value. Okay. And Yongzheng actually did mention that in her paper in terms of, if you include the Magellanic System, what happens with some of those mass census. And many people just don't like the mass stuff at all, right? They just think, this modeling, getting the total mass is dodgy in any case. So, but it doesn't change the fact that the Milky Way is weird in terms of when you look at the densities that you're detecting, and then Hannah's results in terms of where the covering fraction and such.
Thank you.
Greg?
Thanks. Great talk, Mary, as always. The idea I wanted to ask about this flare disk idea for hiding the carbon-4 in the Milky Way. And as you know, well, there's a number of people who have, from the cosmological simulation side, found this result, which is that there's a significant, or seems to be a significant amount of gas coming in, particularly cold gas, coming in sort of coplanar. Daniel DeFilippis, for example. So my question is this: what about Andromeda? Can you? And I guess this is not exactly your work, so I apologize, but. And I guess the Magellanic Stream confuses things, but I was just wondering, I was trying to look at that image that you showed and decide if there was any hint of that. I don't know if you've thought about that.
That's really interesting, Greg. I'm just thinking out loud. So one of the problems is the inclination of Andromeda is not optimal in terms of if it was a flared disk, it would almost, it has to be huge, right? This huge flared disk they're talking about. So it would almost cover, I think, almost that same area, but I think that might be worth looking at. It's yeah, so maybe someone should look at that. And yeah, I'd love to see, especially if people got sightlines on that other side along the major axis of M31. I think that would help things a lot, because the confusion on where most of their sightlines is huge.
Let me just say one other thing. Sorry, Alberto. The magnesium-2 absorbers also seem to find this sort of flared disk picture, but interesting enough, they also seem to see, in the sense that they have absorbers which are at low inclination, you know. So I'm thinking of the
the Ho and Martin work.
Yeah, that's right.
Yeah.
But they also seem to find absorbers which are along the minor axis, so which might be interpreted as outflow. But those don't seem to be showing up in the Milky Way sample. Is that right? Like,
so the magnesium-2 absorber, I would say no, just because the magnesium-2 absorbers are generally that higher column density gas, cool gas that we don't find a lot of at large distances from the Milky Way. Yeah, I would say no offhand, but again, maybe that could be looked at a little bit more.
thanks.
Go ahead, Alberto.
Yeah, so a couple of things. One is that did you try to fold in the star formation, the resolved star formation histories for the local group doors? Because I imagine that between that and Gaia orbits, you could do get a very good idea of where the gas is being stripped, no?
Yeah, so just a tiny bit in terms of, and you know, most of those with the proper motions are also these tiny puny things that stopped star formation a long time ago, right? So that could be an argument either for reionization or that they lost it on first infall, which there's a Fillingham paper consistent with that. Yeah, so a little bit, but we started to bring that in at a larger level. Jan actually we co-eyed an NSF proposal to think about that more. That didn't fly, but I think going beyond that, we'll leave that to other people. I do know Filippo Fratinelli mentioned at the KITP meeting that to me that he was also looking into this. So he may be thinking about that in terms of also bringing in the star formation histories.
Great. And so my other question was that you had a very definite zero for high velocity clouds in the mass budget, I thought. And
that is from Jessica Works plot, and I think she thought she was being funny, you know, just to put that little zero there. And when she said that, she's just thinking of the cold H1 HVCs, right? Which, I mean, she's right. It might be like, it's like a few by 10 to the 8 type thing. So it's, you know, nothing compared to everything else.
So, but I mean, I guess when there was a discovery of a few clouds close to Andromeda, etc., some people got excited, no? And I don't know, I haven't actually followed much the work of the deep H1 surveys, at least in the close to Andromeda and the more extended things. So I don't know what the constraints are, but you're saying it's insignificant.
Yeah, so it's not much mass by any means, but it's also true that this doesn't mean they're not still interesting, because they very clearly represent kind of the cooling probably of that CGM gas. And in particular, what's been found in the halo gas survey and other surveys are not finding large amounts of gas far out, but you know, there's this beard that's been found for a while, and then, you know, maybe a few features, but not much. And there's a Sanchisi review that pointed out that all the larger features were associated with some type of satellite. They thought that's like a conference proceeding, so that's a tough one to track down. But it is consistent with everything I've seen. So that's what we're getting for the coldest component. There was some work recently that I've been asked about. I haven't looked at it super closely, but I think they just smoothed too much, where they do claim to detect some gas in H1 emission further out. I need to look at that work more closely, but I was a little bit, I've seen this before where people over smooth and they start bringing in, the same thing happened with M31 work way back when. Yeah, I need to look at that work further.